Unit commitment. In this section, we will go over the basics of unit commitment and optimization. When we consider the basic optimization problem, we have the minimization or maximization of an objective function subject to a set of constraints. In this case, the problem formulation is the minimization of system costs or the maximization of societal benefits. The system costs we consider are operational costs and startup shutdown costs. These are subject to constraints such as energy balancing, technical limits, and system security requirements. We will go over all of these in more detail over the next few slides. For operational costs, we consider variable costs such as marginal heat rates, variable operation and maintenance charges, fuel prices. The cost minimization will also account for bids, markups, and penalties, such as penalties for unserved energy, dump energy, and soft constraints. Startup and shutdown costs can also be accounted for by modeling fuel consumption at start, operational start and shutdown costs, and detailed start profiles. The objective function described is subject to a set of constraints. This includes the energy balancing constraint, as the aim is to have the generation meet the system's demand. Other technical constraints can be found on the different classes. For example, generator technical constraints such as ratings, min stable levels, min up and down times, cooling states, start profiles, auxiliary services, and individual emissions limits can be defined. Examples on the transmission side include setting thermal limits on a line and interregional exchange limits on groups of lines. For system security requirements, these are accounted for by defining reserve requirements for different types of reserve, such as spinning, non-spinning, and replacement. The user can include additional constraints for resource availability like hydro resources, fuel availability, and financial contracts. Security-constrained unit commitment can also be modeled, which finds the optimal unit commitment and dispatch solution subject to the transmission being feasible if any defined contingency, such as the loss of a line or generator, should occur. To go over the problem formulation in a little bit more detail, we will use a simple example. We consider the system shown, which has 2 generators and a load. The aim here is to find the optimal combination of dispatch from generators G1 and G2 that imply both a feasible and optimal solution in terms of the total system costs. Note that the generators each have their own capacity and cost associated with them. The total load for the system is 250 megawatts. In considering our system, first we have our decision variables, x1 and x2. These represent the load met by generators G1 and G2. We then have our objective function to minimize the system costs. For G1, the cost would be $15 per megawatt hour times the load met by G1. For G2, the cost would be $25 per megawatt hour times the load met by G2. Our total system cost is a summation of these two terms. Now our objective function is subject to a set of constraints. These include the energy balancing equation, that the generation of G1 and G2 should meet the load of 250 megawatts, and the technical limitations of the 2 generators. Each generator has a max capacity defined, so in our simple setup, we have G1's load can be between 0 and 200 megawatts, G2's load can be between 0 and 150 megawatts. This is our problem formulation. Let's consider this pictorially. Remember, our aim is to find the optimal combination of dispatch for G1 and G2. So we are looking for a place on this plot where x1 and x2 give us a feasible solution while minimizing the system costs. But we have constraints to consider. First, we have the technical constraints of the generators. Gen 1 can only operate between 0 and 200 megawatts, so now our feasible solution lies to the left of this blue line. Gen 2 can only operate between 0 and 150 megawatts. We now have a feasible region in the lower left box. A point outside of this box would violate the operational constraints of one of our generators and thus would not be a feasible solution. But we have one additional constraint to consider, the energy balance equation. The solution must exist on this line to exactly meet the 250 megawatt load. Considering all our constraints, we see that the feasible region is in fact this line within that lower left-hand box. But where on this line is the optimal solution? Here we need to consider the objective function, the minimization of system costs. We can plot a small value for the system cost, which lies outside of the feasible region and is represented by the red line. The optimal solution is found by sliding the red line upwards until it finds the first point in the feasible region. This is the first point in the feasible region, which also gives the lowest cost. So this is the optimal solution where G1 has a load of 200 megawatts and G2 has a load of 50 megawatts. A quick sense check, and this is to be expected, as G1 is significantly cheaper than G2. In the previous example, we considered generation levels as continuous, so a generator could operate between 0 and its max capacity. But in reality, that's not the case. For example, G2 would have a min stable level, or MSL for short. The MSL and max capacity define the lower and upper bounds of the generator's operational range. But notice that this introduces a discontinuity. So in the problem formulation, we must introduce integer-type variables to handle this. The new decision variable that we introduce indicates if the unit is running or not. Let's call this y2, and it is binary, 0 or 1. We can now define the operational range of the generator with the equation provided. So MSL times y2 is less than or equal to the load of G2, which is less than or equal to the max capacity times y2. In other words, when y2 is 0, the generator is not running, and the load x2 must be 0. When y2 is 1, then the load can be between the MSL and the max capacity. Note that this setup is now a mixed integer problem to solve. Here we reconsider the problem formulation in more depth. For the objective function, we have the minimization of total system costs. These costs include operational costs, which is the fuel cost times generation output, plus the start cost, which is the startup cost times that startup indicator. This is subject to the set of constraints, including the energy balance, generator operating range, and any other unit constraints such as min up and downtime, ramp rates. So the problem has decision variables that are continuous and other decision variables that are integers. In review, we have some typical attributes that require the use of integers in optimization problems. They include min stable level, min up and min down times, start and shut down cost modeling, non-convex marginal heat rate functions, forbidden zones, regulation ranges, startup profiles, non-convex opportunity costs.